Welcome back. This is Matt DMAT. This is day 15, Monday. We're doing chapter 3, section 2, which is quadratic equations, functions, and zeros, as well as inequalities. Because we've done inequalities before, but that's on a number line. Now we're going to have inequalities of equations, x and y. So it's going to be on the both x and y axis. And we're going to look at inequalities of quadratic equations and absolute values. So things will change now. So what is a quadratic equation? If you would have followed my instructions and 3 weeks ago memorized the library of functions, you would learn that the quadratic equation looks like this. Its graph is a parabola. The lowest point or highest point is called the vertex. We have two forms in which we can have quadratic equations in. This is the standard form. And that's simplified form. They both give us the same picture, except one can do a little bit more than the other one. Remember when we dealt with circles, we had an equation that looked like this. X squared minus h squared, x minus h squared plus y minus h equals r squared. Where was the center of that circle? HK. That's what this one does. This equation, if it's in this form, it'll tell us where the vertex is. Remember, if it's inside the parentheses, it's always the opposite of what it's in there. The outside, it is what it is. If it's positive, the answer is positive. If it's negative, the answer is negative. But the inside the parentheses is always opposites. This equation tells us other stuff. AX squared is called the leading term. The leading term of any polynomial and any equation is the term that has the highest exponent. Largest exponent. That's what makes up the term. The A in front is called the leading coefficient. it tells us the direction of the graph and the shape of the graph. What I mean by that is in last section, we did transformations. So if a is an integer, if a is bigger than 1, then the graph will be much skinnier. It's a vertical stretch. If a is a fraction, then our graph will be squished. It's a vertical compression. It's a shrink. That's what we did in the last section of the last chapter. This actually should be absolute value of a, because the size of it's important, not. So if it's the integer is greater than 1, then it's tall and skinny. If the integer is between 0 and 1, like a decimal or a fraction, it's short and fat. If the value of a is positive, it opens up. If a is negative, it opens down. So that's what the leading coefficient tells us. This number here is called the degree. In this, the simplified form, there's the degree. The degree tells us whether the end behavior of the graph points in the same direction or opposite directions. In other words, does it look like this or does it look like this? I'm gonna give you a spoiler alert here. All even degrees look like this. They point the same direction at both ends. Both ends of the graph either point up or point down. Odd degrees point in opposite directions. So like, in other words, if we had x cubed, it would look like that. X squared looks like this. X to the 9th would look like this. X to the 20th would look like this. Now, it all depends on your coefficient. If it's positive, it points up. If it's negative, it points down. If it's positive, it's an increasing function. That means the right-hand side goes up. If it's negative, then the right-hand side goes down. This is if A is negative. This is if A is positive. Another thing the degree tells us. The maximum number of solutions. Okay, when I say solutions, I mean x-intercepts. And the reason I say maximum number of solutions, I'll show you that in a second. And it also tells us the maximum number of vertices. Let's see what that means. So if we had x cubed, I'm going to exaggerate this graph. That means, remember, this thing tells us we can have 3 solutions. And it's odd, so it points different directions. Since it's positive in front, it points up to the right. So we can have 3 solutions. Or we can have 2 solutions. Remember, where it's touching or crossing the x-axis, it could be 2 solutions, or this one's 3 solutions. Or we can have 1 solution. Odd degrees have to have at least 1 x-intercept. Because the ends point different directions, one of them, one direction is bound to cross the x-axis. So the most you can have is your degree. When we say degrees, I'm going to use the letter n from now on. So if we had x to the power n, that's the degree. So if n is odd, we can have as many as you have there. But now look at this. The number of vertices. If you have 3 solutions, how many vertices do you have? 1, 2. 2 vertices. If you have 2 solutions, well, we have that. We have 2 solutions here, our 2 vertices. 2 vertices. Or you can have no vertices. It's just an increasing function. This is the way the graph looks if you just graphed x cubed. So the general rule, the number of vertices is at most n minus 1. Remember, n is the degree. Whatever your degree is, you're going to have 1 less number of vertices. If n is even, let's say x to the 4. Since it's an even, both ends point the same direction. So we can have 4 solutions. We can have 3 solutions. We can have 2 solutions. We can have 1 solution. Or we can have no real solutions. It is possible to have imaginary solutions. Since we have this case, it's a degree 4, we have to have 4 solutions. There could be 4 imaginary, 4 real, or 2 of each. But they have to come in pairs. Imaginary answers have to come in pairs. And again, the number of vertices is always 1 less than the degree. Okay. Let's go ahead and stop there because I see most of y'all falling asleep. And when we do next time, what we're going to do is we're going to learn the quadratic formula. We're going to learn how to complete the square. We're going to learn how to find the intercepts. We're going to start learning how to graph these things. And then in the next section after that, section 3, we're going to start looking at how to interpret. I'll give you the equation. You're going to tell me what the graph looks like. How many solutions will I have? How many real solutions will I have? How many imaginary numbers? And then that's why all this stuff has to be known. So it makes it much easier as we go on. Okie doke.